Hello, and welcome to my first lesson on quantum mechanics, Theory and Experiment. It is based off of the book by the same name by Mark Beck, and this lesson will just go over the mathematical preliminaries to be able to do any quantum mechanics. Basically, we'll go over probability and statistics and a bit of linear algebra. But there's no point talking anymore, so let's just begin. We start off with discrete statistics, meaning just the statistics of individual objects, sets that aren't continuous. So for example, if you have a bunch of measurements, set of measurements x of measurements of I, then the average is just you adding up together all of the measurements and dividing by the total number of measurements. And you can do the same thing for a function average. You just do the function of each measurement and then divide by the total number of measurements, and you get the average function for that value. The average here will be denoted by these angle brackets. And an interesting thing to know that will come up multiple times throughout this book is that averages are linear operators. So if you can apply them individually to these functions, but you can also bring them out and apply an average to the entire thing. Continuing this, we have the idea of deviation, which is just the difference between the current position and the average position. But if you're going to average this out, then it actually becomes 0. So it's not a good tool to understand fluctuations. What you actually can do is construct something called variance, where you just square the deviation and then you take an average of that. However, it's not necessarily a useful tool, variance on its own, because variance is just the square of the deviation. However, if you take the square root of this, then you get what's called standard deviation, which is just the square root of the difference in the average squared of x minus the square of the average position of x. The standard deviation is the standard way to find how much something deviates, or more specifically, how far a particular measurement is likely to be from the average value. And this value can quantify uncertainty within a measurement set. You can also construct probability out of the number of states of x of I and divided by the total number of states. If you're coming from thermal physics, this might be familiar to you as the multiplicity of state 1, or some states of I, divided by the total multiplicity. These ideas are equivalent, however, it just uses different notation and slightly different wording. You can also write averages in terms of probabilities. If you want to work these out for yourself, how you go from the traditional averages that I showed on the last few slides versus these that use probability, it's a pretty easy thing, so I'm not going to show it. However, discrete statistics are only useful for discrete sets. What if you have a continuous set, or a set that is that has so many data points that it is essentially continuous? Then you can use continuous statistics, which use the probability of some x is equal to the probability density times the small change in x. This is called the probability density because it tells you the probability for any given x value. And then when you times it by this dx, you're getting rid of that unit of 1 over x, and so it becomes the unitless probability. Of course, you want to have a 100% probability of getting something anywhere, so there's a normalization of taking the integral from negative infinity to infinity and making that equal to 1. You can construct the same thing as with the discrete summation. The average value of x is just equal to x times its probability density times its change in x, just integrated. Same thing for the average value of a function. Moving on to linear algebra, we have the traditional notation where we just have a vector which has components in the x direction and in the y direction. But moving to more matrix representation, you can write these as row or column vectors, where this is a row vector and this is a column vector. And note that the respective unit vectors would be this for x and this for y. With two vectors, you can construct the inner product. This is its traditional definition, but you can also write this out in matrix form, where you have A as a row vector and B as a column vector. And so it's just the multiplication of AX, BX plus AY, BY, which gives the inner product. It's also called the scalar product because it reduces from a vector to a scalar result. And some of you may have noticed the saying that A as a row vector is the same as A as a column vector doesn't really apply if you're in complex numbers. So for complex numbers, if you have A given as a column vector, then the respective A row vector would just be the flipping of it, the transpose, but then also the complex conjugation of each individual element. Then in linear algebra, we have some cool things called eigenvalues and eigenvectors, which are the values lambda and the vectors x in an equation of this form. What this equation says is that some matrix times this vector x, the eigenvector, will just give back a scaled version of that vector. And so you often get these as a result of physical situations, quantum mechanics, optics, other things. So to solve this, you can set this equal to 0 by moving over the lambda x and then pulling out the x. And right here, this I matrix is the identity matrix. So you're just going to have a matrix that looks like this, and you just have lambda going throughout the middle, and then you're going to just have zeros. And this is, of course, the one I drew is a 3x3 matrix. However, for the example, we're just going to continue going in 2D. So in 2D, it becomes a system of two linear equations right here. And there is a solution to that if the determinant of that system is equal to 0, which is seen right here. As an example, let's find the matrix eigenvalues and eigenvectors for this one. So now pardon me for my shaky writing because I'm not good at writing with a mouse, but the first thing we want to do is find the determinant of the form on the last slide. So we want 0 minus lambda, then 1, negative 2, 3 minus lambda. To take the determinant of this, it's just equal to you have negative lambda times 3 minus lambda, and then minus negative 2 times 1, so you just have plus 2. So this is just going to be equal to negative lambda, that'd be negative 3 lambda, plus lambda squared plus 2. And this, of course, would need to be set equal to 0 so that you can find the correct lambdas, the eigenvalues of the system. You can solve this quadratic equation, and it will give you a form of lambda, and then we'll just say plus minus is equal to, you have negative of negative 3 plus or minus the square root of, it's negative 3 squared, so let's just say 9, minus 4, and then times 1 times 2, so just 4 times 2. All of that divided by 2. And so this implies that we're going to have lambda positive equal to 2, lambda negative equal to 1. So as you can see, there are two separate eigenvalues for this system. Now we need to solve for the correct eigenvectors for this system, and we can do this by solving for each particular eigenvalue. So we have the matrix 0 minus 2, because this is the lambda plus eigenvalue. So you have 0 minus 2, 1, negative 2, 3 minus 2. This matrix times, we want to find the first eigenvector, so I'm just going to say x positive 1, x positive 2. And this, of course, equal to 0. Now this yields a system of two equations, negative 2x plus 1 plus x positive sub 2, negative 2x positive, positive sub 1 plus x positive 2. And these are both equal to 0. And because these are the same equation, we can solve this by plugging in, and we obtain x positive 2 is equal to 2x positive 1. So the eigenvector corresponding to lambda positive is then x positive vector is equal to, as a column vector, x positive 1, 2x positive 1, which is just equal to x positive 1, 2. Furthermore, it's often useful to normalize these vectors. So to find the normalized form of it, we want to divide by its magnitude, set equal to 1, meaning that we want to have x positive squared 1, and then you have this column vector, which when this is squared to find the magnitude, it actually ends up being a row vector times the column vector. So we get the form 1 squared plus 2 squared equal to 1 for normalization. Implies that we have the normalized x vector is equal to 1 over the square root of 5 times just 1, 2 matrix, column matrix specifically. You can do the same thing to find the eigenvector corresponding to lambda minus, but I'm just going to write that out instead of having to go through the derivation. You can do that for yourself and check if you have the correct answer. So here are some problems that you can work on over the next week or two before I get the problem solutions posted as a video. They contain things of just basic statistics all the way up to finding eigenvectors and eigenvalues yourself. I really recommend that if you want to learn all of the material in this book that I'm going to be presenting, that you work through the problems, because it's one thing to understand conceptually, but it's another thing to demonstrate your knowledge through practice. So I highly recommend that you work through these. But thank you so much for watching, and look forward to the next video, which will be the problems solutions for lesson 1, and after that, lesson 2A, where we start our journey in actual quantum mechanics. But specifically, we're actually just going to start with classical optics, so you'll have to wait until chapter 3.